Good morning. I would like to summarize what we had about master equation for discrete state spaces, and then move on to a new chapter, which is going to be the corresponding formulation for continuous sample spaces. So let me recap. For discrete state spaces, but also quite in general, a starting point of the analysis is that we have the Markov property, and that means if you look at the conditional probability, you can dissect it into two parts. The transition probability from state 0 at time t0 to state n at time t can be written as a sum over all the intermediate states. And then you have a product of conditional probabilities of going from initial state to an intermediate state, and from there then to the final state. That's really the basis of the analysis. And then we looked at a differential formulation and found a differential equation, and that differential equation is the master equation, where you have a linear equation for the probability density or probability distribution, and this operator Q then determines all the physics of the system. There's an alternative form of the equation, and this alternative form is in the gain-loss type of form, where you have the first term being the gain of probability into the state n that you're considering, and the second term is the loss term, and you can write this either as the total exit probability from the state n, or you can write it in a form which is more symmetric, like in the second line. All right, so that's something you all know. And then we asked ourselves what's special about these processes and how can we classify them? Well, if you look at irreducible processes in the finite state space, we have learned that there's a unique steady state and all the entries are positive. We have learned that if you go to a reversible dynamics, that this is equivalent to detailed balance. It's equivalent to having no currents in loops, corresponding to the Kolmogorov loop criterion. And when you go back to irreversible processes, then you know they must have fluxes, and fluxes or currents in state space, they are a hallmark of such non-equilibrium irreversible processes. And we also learned that you can characterize the irreversibility of the process by a quantity that we call entropy production, but it's actually just the asymmetry between the forward and the backward trajectories. There's one point I left out up to now. I mentioned it, namely that you can use these concepts to do statistical physics, and it's really the concept to do numerical analysis of statistical mechanics problems. So remember, in classical statistical physics, you can describe the steady state distribution by a Boltzmann distribution, where Z is the partition sum, and then the typical task you're facing is one where you need to calculate averages of observables, and these observables can be any quantity that you would be interested in. So this is something you have to calculate. And that's hard because you have a huge state space. So think of an Ising chain where you have 2 to the n different microstates. So it's very hard to enumerate all these states. And you need an alternative of how to calculate the average or the partition sum. And this alternative is that you use an auxiliary Markov chain. So you define a Markov process that obeys detailed balance, and therefore the transition probabilities are such that the forward and backward transition probabilities, the ratio of that is given by the ratio of the corresponding probabilities, which you can choose then to be the Boltzmann factors as you have them here. And then you get on the right-hand side e to the energy difference between the two states, and I've put here kBt to 1, so the equations are simple. Okay? So that's what you need to do, and there's no choice because detailed balance only constrains the ratio of the rates, but not the rates themselves. And there are various ways people have implemented Monte Carlo simulations, and one quite frequently used method is to choose what's called the metropolis algorithm. And there you choose the forward rate to be e to the minus the energy difference if the energy you're getting into has a larger energy than the energy you started from. So you penalize the transition in the forward direction to a higher energy. And if the energy is lower, you say you accept the move, the probability is 1. Okay? And there are other choices you can use, and that's one where you can really simulate the dynamics of a statistical mechanics problem. And if I were to continue here, I could give a whole course on how you use the Monte Carlo method to analyze statistical mechanics problems. All right, so that concludes the part on discrete state spaces. And now let me move on to continuous state spaces. So now instead of having a variable that's out of a discrete set of states, you now have a probability vector which can take values which are real, and in general you will have a d-dimensional state space that you consider. Just think of a particle suspended in a fluid. That means a particle which by the thermal fluctuations that you have in these systems shows Brownian motion, and then x of t is a three-dimensional random variable. You can have something more complicated. You can think of a rod-like particle like a bacterium, and this rod-like particle, in addition to having a position, let's now think of this in two dimension in the plane. You can have a position variable x of t that's in R2, and on top of that you might want to characterize this rod-like shaped particle, a bacterium for example, also by an angle variable theta of t that is out of the interval between 0 and 2 pi. You can make things even more complicated. So you can think of a bunch of particles, many of them, and then the description of those will be in terms of a density and maybe also a velocity field that depends on space and in time. And then you will have to formulate a stochastic theory, not just for variables in RD, but for fields. Okay? These are now fields, and they need to be treated as random field variables. All right, so our goal in the end is that we want a time evolution equation for a probability density. So we want it for p of x and t, given that I have some initial condition x naught and t naught. Okay, so time evolution for the transition probability densities. And that's in general a modeling problem, because now you have to look at a concrete physical system and you have to decide how you would like to describe it. So let us talk about this a bit before we go into the math and go back to the slides. So when you talk about continuous processes, one example which is quite instructive, and we've talked about that, are molecular motors. So these molecular motors, they are walking on filaments, on biopolymers. Here this is a microtubule, and this is supposed to be a kinesin motor with its two heads that are actually functioning as legs. So as you will see in this animation, this is not a simulation, but really just a visual illustration of what's going on. So you have those two heads that can bind to the microtubule, and as they bind, there's complicated biochemical processes that happen. In particular, there is a chemical process which is the transformation of ATP into ADP, and this whole process repeats again and again. And as you see from this illustration, a lot of the elements of this molecular motor are in motion, and a lot of things happen here that drive the mesoscopic or microscopic motion of this motor along the microtubule. Now, how would you describe such a motion? Right? You could say, well, let's really look at the proteins and look at the amino acids, at the details of the molecular process. And then you would need something like quantum chemistry or molecular dynamics simulations to really embed in such a simulation the whole detailed dynamics of such a process. And to some degree you can do this. This limits you to certain time scales and length scales because these simulations take time. And there's the same problem there because you need to decide on what molecular level you would like to describe the process in. So there's always a problem of coarse graining that you have to solve. And if you remember what we did in the early part of the lecture, we said, let's look at this in a very simplistic way. The microtubule is a one-dimensional lattice. And then let's idealize this motor, the kinesin motor, by a particle. And this particle hops forward by a constant rate. And that gave us the Poisson process describing such a molecular motor. Okay, so we had an idealized Markov process that describes that. And we found from that analysis that the randomness ratio is 1, and that doesn't quite describe the data. These are data here. So here you see data from Karel Svoboda when he was in the groove of Bloch. Here is time, and these are different trajectories of such a molecular motor along a microtubule. What you should notice is that in addition of this looking kind of step-like, you don't really see the steps much here. There's also quite some noise that you have here. So this is rather random in terms of the trajectory that you see here. And you have to ask yourself, where does that come from? Well, it comes from the fact that you don't really look at the motor itself. You have on the motor attached a big colloidal particle, so a plastic bead, and you're observing this plastic bead. And that by itself shows Brownian motion. Okay? So superimposed over the stochastic trajectory that you have that describes the motion of the molecular motor itself, you have the random Brownian motion of your measurement device that's hanging on to the molecular motor. And that's what you see here. This is basically random Brownian motion in a potential because that bead is connected to the kinesin motor. Question then is how you describe that, right? So this here, in our idealized representation, was a discrete state space. You had jumps from one lattice side to the other. The random motion of a bead suspended in a fluid is more like a continuous state space where you have continuous variation in R3. Okay? So it's a combination somehow between discrete state spaces and continuous state spaces, and it's a priori not clear what kind of modeling level you choose when you describe such a phenomenon. Let me give you another example. This other example is a famous experiment by Howard Burke, which has been repeated by others. So what you see here, there's a movie that I'm going to run in a second. What you see here is E. coli bacteria, and they have flagella. So you can see them here, they're pretty faint. And these flagella propel the bacteria in space. Now let's look at the movie. So you'll see as these bacteria move, they have phases where they move straight, and they have also phases in their motion where they kind of stay in place and tumble. Okay. So let's idealize that in a cartoon picture. So in this cartoon picture, what we just saw in the experiment was that on the scale of observation in the time and space window that you saw, there's some run motion of bacteria, then they stay in place, they wiggle around, change direction, move for another trajectory, then they tumble again, they run and they tumble again. Okay? So you see there's, if you look at this from the perspective of such a description in terms of position and orientation, the orientation is fixed for a while and then jumps from one orientation, so this one here, to another one. So it seems like this theta is a discrete, it's a continuous random variable, but it shows discrete transitions between different states. If you look at large scales, so you kind of take a large picture of the motion of the E. coli over a large time and space window, then the trajectory will have many turns, and it looks more like a random walk. And indeed, as we will later show, in the limit of long times and large number of tumble and run events, the process that you see converges to a random process, which is a Brownian motion process. So how does that all fit together? You have discrete steps, you have continuous Brownian motion. How can we mathematically disentangle all these processes, right? And that's what we want to do today. And for that, we need some mathematical background. We need to specify what we mean by a continuous sample path and what we mean by a discrete sample path, right? I've been using this in a rather metaphoric way, describing the experimental data, but what is it mathematically? So let us define a continuous sample path. Here we have the conditional probability that you are at position x prime at time t, and you hop to x at some small time increment later. Continuous sample path now means that if this jump is larger than some arbitrary positive value epsilon that you choose, that the limit of 1 over delta t of this is 0. And that means intuitively that you don't have discontinuous jumps in your trajectory. It's very unlikely that you have a finite jump of finite length larger than 0 in finite time. Okay? A very famous or paradigmatic example is a Gaussian process, or a Brownian particle. And here you have, for the conditional probability, a Gaussian distribution, and you can do the math, and you will see that this has a continuous sample path according to that definition. So what it means, you have continuity. It doesn't mean that you're smooth, right? It can mean this trajectory can be as crazy as possible. It has to be continuous. It does not have to be differentiable in any means. The other case, a discontinuous sample path, is one where you allow for finite jumps. So you say that the limit of delta t going to 0 of the transition probability from x prime to x in a small increment of time, delta t, this is going to be a finite quantity. Okay? So there's a finite transition rate, w, between the two states that describes that process. This would be 0 for a continuous process. There would not be such a transition rate between two states. A famous example also is the so-called Cauchy process. It has, instead of this Gaussian distribution, it has a power law kind of tail in the outskirts of the probability density. And as you do the math here, you will see that this quantity does have a finite transition rate W. All right, so let me start then writing down what you get for the dynamics of such a process. All right. So what we want is we want a description of an observable. Let's call it F. And you want to know how this observable F evolves in time. So you can write this by its very definition. This is an integral of the observable that I'm interested in times the conditional probability of my dynamics. If I were to be pedantic in notation, I would indicate here that this is an average for a given initial condition x naught at t naught, but I'm going to omit this just for simplicity of notation. Okay, so we have this. This would be the equation of motion for an arbitrary observable. And now I can use the representation of the right-hand side in terms of a difference quotient. So this object here is the same as the limit of delta t going to 0 of 1 over delta t, the integral over space, f of x, and then in the brackets, I'll have the difference p of x at time t plus delta t, given the initial condition, and I'm going to be short here, I just denote the initial condition by the simple dot, minus p of x and t given the initial condition. So how do I proceed? Well, this object here I can write in a different way using the Chapman-Kolmogorov equation. Okay? That's a similar procedure as we've done for the master equation. And here I can write it in a more complicated way by inserting a 1 here. Okay? So let's do that. This is then the same as the limit of delta t going to 0, 1 over delta t, integral over x, f of x. So and here I'm using then the Chapman-Kolmogorov equation. So that means I need to integrate over some intermediate time point, p x t plus delta t, conditioned on the value at some time t. And then I need to continue with p of that intermediate point and then conditioned on the initial condition. Okay. That is using the Chapman-Kolmogorov equation, where you insert here this intermediate point. And for the 1, I'm just saying that this is then minus the integral over d x prime p of x prime t plus delta t given xt, right? This is a 1 because I'm integrating over all possible outcomes of this conditional probability. That's by normalization 1. And this is then times p of x and t conditioned on the initial value. All right. So it's the same idea as for discrete processes. You want a differential equation, then you have 2 points which are close in time. For those points that are close in time, you employ the Chapman-Kolmogorov equation, and we go from there. All right, now let's look at 2 special cases. The first special case I want to look at is what I call a jump process. And that means I'm going to assume that this object W x prime x at time t, so the transition rate from x to x prime exists and is given, as we had it on the slide, by the limit in terms of the conditional probability densities x prime t plus delta t conditioned on x and t. So we say this is existing and there are no continuous parts in the stochastic process. That's why I call this a jump process, or let's say a pure jump process with only these kind of transitions. Well, then the analysis is quite straightforward, because when you look now up in the expression that we have here, right, it's this limit 1 over delta t. And if you look here, this quantity that you have there is just the definition of a transition rate. And the same on the other side. Okay, so here I can just read off from the definition of this object that this is equal to an integral over dx f of x integral over dx prime w x comma x prime at time t, sorry, x conditioned x prime at time t, p of x prime and t, conditioned on some initial value. Right? This is just taking this here and taking the limit delta t to 0. And in the same way there, this is then minus w the other way around, x prime conditioned on x at time t, and then p of x and t conditioned on the initial condition. Okay, now this is valid for any function f, right? So it's valid for the probability distribution itself. And that means now we can write our first result. And this first result is that the time evolution of the probability density is given by this structure, which is really the same in structure as for the discrete process. All we have changed is that we have replaced the sums by integrals. Here's a gain term. You start from position x prime at time t. You transition into x, and that gives a gain in the probability density. And here, this is the other way around. Here you start from x, go to any kind of x prime, so you lose probability out of the position x. Okay. So it means you have the same functional form, the same form as for a master equation for discrete state spaces. Okay, so here the state space is not discrete, the state space is continuous, but the sample space the trajectory space is discontinuous because you have those jumps. And that's why you basically get the same structure for the equation. All right, that's one limit. The other limit we can look at is where you say you go the other extreme, you just have continuous sample path, and you don't have jumps at all, and that's called a pure diffusion process. So what I'm doing there is I'm assuming I have a continuous sample path, and I'm now defining moments, and you'll see in a second why they are useful. So I define a vector of first moments as the limit of delta t going to 0, 1 over delta t, and here I'm now integrating over x prime, and I want the difference xi prime minus xi p of x prime and t plus delta t conditioned on xt. Okay, so what is that? It's just the expectation value of the difference between the point you start and any other value you can get into. And that you can write in shorthand as an average of delta xi, right? Delta x being x prime minus x over delta t in the limit delta t going to 0. So it's the speed, the typical speed of this stochastic variable. If you think of a Brownian particle, maybe it's a good picture to have in mind. You can have a Brownian particle subject to Brownian motion, but also subject to some external fields, like an electric field or some kind of other force that you apply to it, and that will be the deterministic part that comes from this driving force, external driving force. I can also define higher moments of the conditional probability density in a very similar way. I take the limit of delta t to 0. I want 1 over delta t, integral over x prime, and then I'm looking at xi prime minus xi times xj prime minus xj. In the same construction, I'm doing the average over the conditional probability in some small time interval delta t. And that you can write in a similar fashion. This is delta xi, delta xj averaged over delta t, again in the limit of delta t going to 0. And obviously the higher moments, right? You can continue this. You can look at the third moment, the fourth, the nth moment. And my assumption will be that all these higher moments vanish. It doesn't mean the moments vanish. To be precise, it says that the moments will not scale like delta t. They will scale with a different power in delta t, such that the limit where I divide the moments by delta t goes to 0. Okay? That's what I mean. All higher moments that I construct in a similar fashion, I assume to vanish. Good, that's my assumption. And now let's see what I can do based on that assumption. So we proceed based on that assumption that we have here with this equation. Okay, so we do have, as before, this general starting point. I want the time evolution of an arbitrary observable, and by using Chapman-Kolmogorov, I can use this identity here. Okay. Good. Now, let me do a trick here and rewrite this a bit. So I'm going to copy it here on the board. I have dt f at time t is given by the limit of delta t going to 0, 1 over delta t. And I'm splitting up the terms. So the first one is an integral over dx and an integral over dx prime. And so here you have dx and dx prime. They're both dummy variables, x and x prime. So I can just rename x to x prime and x prime to x. So that means we have here f of x prime. Then I'm renaming here this as well. So I have p of x prime at time t plus delta t, conditional on x at t times p of x prime comma t, conditioned on the initial condition. And for the rest, I just leave it as is, right? So I take the same expression as this one here. Okay. Now I'm going to do a Taylor expansion. Of f of x prime with respect to the position x. So imagine doing this. The first term of the Taylor expansion is f of x. Now f of x, if you take this here, right, this term times that term is exactly the 0th order term of the Taylor expansion. Okay, so it cancels. Okay. So what you see is that the 0th order term cancels with this last term here. So what I'm left with from the expansion is the first Taylor coefficient, the second Taylor coefficient, and the third Taylor coefficient. And now let's just write this out. So this will then give the limit of delta t going to 0, 1 over delta t, a double integral over x and x prime. Then let me take a bracket. I will have from the Taylor expansion xi minus xi prime minus xi di of f evaluated at position x times our conditional probability at x prime t plus delta t conditioned on xt and p of xt conditioned on our initial condition. That's the first term I get. And as the second term, I get a very similar structure. I just have now the second Taylor coefficient. So this is the product of xi prime minus xi and xj prime minus xj. And I have here then a half times di dj of f evaluated as x. And I copy the same kind of expression as I have above. So it's a lot of writing here that we have to do. But basically, all I have done really is to do this Taylor expansion, which is this term and that term. I have here written an equal sign, while actually I should have written plus higher order terms, which are higher order moments. But now the assumption comes in, right? I'm saying that I have only those two moments being finite and all the higher moments actually vanishing. So I don't have to consider them here. They vanish in the limit of delta t going to 0. And you see, right, this here maps with the definition of the first moment, and the second term maps with the definition of the second moment. Okay, so if you write this then out, this is equal to the integral over all space. Then I have dif ai of x and t, p of x and t on the condition, plus a half di dj f, and the second moment, bij, x and t, p x and t, conditioned on our initial condition. All right. Now, to have the same argument as before, that this is valid for the function, arbitrary function f, I need to rewrite it a bit, namely such that I have the function f isolated and all the derivatives acting on the complement of the corresponding expressions that you have here. Right, so as you do partial integration, you can make these operators that you have here act on the right-hand side. We neglect any kind of boundary terms, and then we can use the argument that this remains valid for any function f. So from that, then finally, you arrive at an equation for the transition probability density. It's minus di. This minus comes from the partial integration. And I'm acting here on the first moment, also called the drift vector. Times the conditional probability density plus a half di dj Bij x and t p of x and t conditioned on the initial condition, and that's called the diffusion term for reasons that we will see in a minute. Okay. And this equation has a name. This equation is a Fokker-Planck equation. So we have everything in place now. We do have two sets of equations that you can derive for systems that have a continuous state space. If you have jumps, in a pure jump process, you get this equation that has the same formal structure as a master equation, just with integrals instead of sums. For a diffusion process, where I assume the first two moments to be finite and the other higher moments to vanish, I get a partial differential equation. This is an integral equation, right? This is a partial differential equation that has on the right-hand side a term that's linear in the derivatives. That's called the drift term. We'll see why. And the second term is the diffusion term and contains second-order derivatives. Well, you can also see why this is called drift and diffusion just from looking at the definition of the moments. This is the average speed of my random variable, and this is the variance of my random variable. If you have isotropic space, then you know that delta x squared for a Brownian particle is proportional to delta t. So this is then going to be a diffusion coefficient. All right. Yeah, please.
What's the relation between these moment functions and the correlation functions?
Between what?
Correlation functions.
That's something you can calculate. A correlation function would be you have an observable A, like the position of a particle, and at a certain time, t, and the position of the particle at a certain time, t prime, right? And then you could calculate the corresponding correlation function between the two positions. Okay? And that's not the same as this here, because this here is for small time increments. Okay?
A and B can definitely be expressed by correlation functions.
If you do have some observables, let's call them A and B, then you can calculate correlation functions if you know the solution of the Fokker-Planck equation, because you need the probability distribution function in order to calculate the correlation function. Right? So if you have here an example where x of t is from R3, and you want to know the correlation function of the position of my particle between two times t and t prime, I and j, then you can calculate this, because from solving the Fokker-Planck equation, you know what these brackets mean. Okay, the difference of that object, this correlation function, to here, there's also a correlation function, but that's a correlation function for incremental time. And for that, you can derive the corresponding mathematical expression. For this, you need to solve the full equation. Other questions? Yeah?
First line, the upper right of the blackboard, I think the last term has an extra term, like p, should be px, t condition, initial probability.
Didn't I do this?
Only the first line there is an extra term. Yeah, I mean.
Didn't I do this?
Yeah.
Right? This is conditioned on the initial condition. That's this dot here. And that's also conditioned on the initial condition. That's this dot here.
Yeah.
Yeah?
What is the type of the very first line?
In which one?
In the very first line, second, yeah, that px prime at the end should be px.
Oh yeah, thank you. Because I switched x and x prime, I didn't do this there. Thank you. Okay, so let's summarize this maybe. So what you can actually do, and I didn't show this, that you can do the mixed case where a sample path has discontinuous parts and continuous parts. That's quite an involved mathematical analysis, not because it's difficult, it's just a lot of writing that you have to do in proper limits. And the outcome of this analysis is something which you could have guessed, namely that what you have is that for a general process, you just add up the two parts that are just derived. There's one part coming from a diffusion process. This is with a drift vector and a diffusion matrix, and the other part describing the discontinuous events during the process is given in terms of the integral equation that looks like a master equation. And if you want to see how this works in detail, just look up my lecture notes or some other book where this is described in very detail. Yeah.
If we have a special boundary condition, can we still get a Fokker-Planck equation? Because we need to use integration powers.
Yeah.
So if there's a special boundary condition, do we still get the Fokker-Planck equation?
You can always go to the boundary that those terms don't matter, and I can show you later how this works in detail. The boundary conditions come in once you solve the equations. These boundary terms, they don't matter for the function, for the derivative, because you can choose the function f as you like. And you can make it such that these boundary terms don't vanish. Of course, if you do something crazy, which typically doesn't happen in physics, you can mess this up. But in general, this works. Yeah. All right, so that means these equations, in the same way as the master equation, are the foundation of analyzing continuous state space random processes. Okay, and this partial differential equation form here is quite reminiscent to other partial differential equations that you might know. For example, Schrödinger's equation. Structurally, it's very similar to that. Okay? And this term here is something that comes from the discrete part of the process. And it's actually not so easy to solve these equations exactly. We're going to learn that you can analyze these equations in terms of eigenfunctions in the same way as you decompose the Schrödinger equation into eigenfunction. That's a useful tool here as well. And we're going to learn that you can rewrite this Fokker-Planck equation in a form which is called a Langevin equation, that looks again at the trajectories and not at the probability distribution function. We had this before for the master equation. You can look at the master equation and solve for the probability distribution function, or you can look at the Gillespie algorithm, and the Gillespie algorithm gives you each of the random trajectories. And there's an analog here. You can look at this, or you can look at something that gives you the individual trajectories that you can analyze. All right, let's have a break.